Well, good evening, ladies and gentlemen. My name's Nigel Shadbolt. I'm Principal of Jesus College, a Professor of Computer Science here in Oxford, and recently appointed Chair of AI at Oxford Research, one of whose ambitions is to understand the range and depth, the remarkable spectrum of work underway in AI, its fundamentals, its application context. So there is a wonderful opportunity here tonight, both to network and to hear about the opportunities for AI in science and indeed philanthropy support. So it is a great pleasure to introduce our speaker this evening, Professor Stuart Feldman. There are very few people whose work can genuinely be said to have shaped the daily practice of computing for generations. Stuart is one of them. As the creator of Make, one of the most influential software tools, I might say, written, he developed a system that became fundamental to modern software engineering. And the ACM citation for its Software System Award remarked that there's probably no large software system in the world that has not been processed by a version or descendant of Make. That's a pretty remarkable claim. But that achievement just is one chapter of an extraordinary career. Stuart was part of the Bell Labs environment that created Unix, helped create Unix, contributed to the first Fortran 77 compiler, led major research and engineering organizations at IBM and Google, and served as president of the Association for Computing Machinery. And today leads Schmidt Sciences, where he's helping shape new models for supporting scientific discovery itself. And I should say, has been a wonderful supporter for science at Oxford. Schmidt Sciences fund £13 million of funds to MPLS alone. AI in science postdoctoral fellowships. £5.5 million for the faculty AI in science fellowships. 45 postdocs and 6 faculty fellows. Really wonderful investment in some of our brightest talent. What makes Stuart particularly well placed to speak on AI and science is that he's lived through and helped shape several of the great transformations in computing, from programming languages and operating systems to large-scale software engineering to the emergence of modern AI. Few people possess such a broad perspective on how advances in computation become advances in science and society. Please join me in welcoming Professor Stuart Feldman.
Probably, yes, I think it is. Okay. Yes, it's embarrassing to have written a piece of software that is still being used 50 years later. This says something about some aspects of the field, but let us not go there too much. Okay, so let me just start. Let me see. Okay, fine. So I have, as always, far too many slides, so I'm going to just march through a number of them and let you can read the text or not as you wish. But there's only one equation and it's illegible. Let me see. I guess I have to be this close for it to work. Thank you. Near field mic, not a far field one. So basically, I would like to discuss the state and guesses about what AI will do for and to science. I'm not going to focus much on the general story of AI versus society versus or AI will eat your soul and all of those other topics. Yes, I can discuss those too. I don't actually think it's going to do the soul eating, at least. However, theology is an older science, so we'll worry about that separately. But the quick summary, is the best of times, the worst of times. We are at the beginning of a possibly wonderful transformation of how we do science, the speed with which we can do far more amazing things. But as this happens, it's going to change the practice of scientific research, the practice of education in science, ranging from the junior schools to postdocs and PhD students, or whatever those roles will be in 20 years. So I will comment on some of these things. Let me just be careful. I normally bring an extra prop of a broken crystal ball to show that, don't trust any forecasts, but you can at least be either entertained or in the Q&A section throw your corrections. Thank you. So anyway, basically this is a new aspect of doing scientific research. The modern AI revolution, not to be confused with several previous tries, is really having a huge impact on what people can do. Yes, there are areas which are clearly overhyped, but there are others which are not yet fully understood. It's also very expensive, very costly to play this game. We are in the process of negotiating to buy for various support of scientific research couple $100 million worth of computers by the generosity of the Schmidts. So that will be the next game. But I'll answer any of the questions on the AI threat or menace topic later. But I will hope that we can discuss possibly later what you think is going to happen to you as students, as young researchers, and as mature researchers. There's different impacts. So what are some of the implications? Well, AI is already here in some fields. I will probably not bother reading a paper on computer vision or natural language processing that does not discuss an AI piece, because it's obviously irrelevant. Those fields have just been overrun with new techniques in practice. I was at Google when the natural language processing revolution happened, and during a 18-month period, a lot of wonderful software got tossed completely. Don't need hidden Markov models anymore. They were all replaced by early machine learning over an 18-month period with an amazing improvement in every simple performance metric. And it was just amazing to watch it happen sort of while you stood in the hallway. Okay, sometimes revolutions are real. And it was 18 months before 40 years of research was tossed in the bin. Yes, my friends have been doing HMMs forever, all gone. We expect it to affect the understanding of science itself. What will the future and current advanced AI systems do for your understanding of science and for your assisting you, or possibly getting ahead of you? A serious problem, which I'll try mentioning later, is what if your computer knows more than your beginning graduate students? How do you manage the traditional training and discipleship of getting people from starting PhD students to being experts and deep acculturated? Well, it's going to be really hard. So basically, we're already seeing plenty of examples of cheaper, better, faster. Yes, you can get all of them today. It's not a trilemma question as is usually posed. On the other hand, this depends on somebody else paying for your GPUs. Otherwise, cheaper isn't a given. But AI is going to exacerbate trends. I'll try to discuss some of them. But you can go down a list of areas where AI is clearly a productivity boost. It's the doing of science, everything from workflows and automation to literature searches, data acquisition, curation, analysis, calibration, cross-checking. AI systems are already extremely active or superior in many of these. You are crazy to do a literature search by going down to the library and looking for nice bound paper journals. unless you are in a medieval history. Oh, by the way, we do support research, AI research for things like medieval history as one of the things Schmidt Sciences does. So, but the theoretical exploration part I'll come back to. That is a much more interesting topic. What is the modern role of theory? How do you understand it? So, a key way to look at this is, just simple critical economics. If some factors of production become much less expensive, then others become relatively more expensive. 100% doesn't change. And you also end up always with Jarvan's paradox. If something gets cheap, you buy more of it, and you use more of it. That's the paradox that says you never win by building more roads. They fill up before you expect it. Well, same with computers. But there are all kinds of implications for advanced education, and by advanced education, I will count everything that's done here, anything from undergraduate through junior faculty. The traditional modes of education involve having junior people do hard things, the equivalent of washing the beakers and adding up the columns, and that's been improved over the past decades. So now you wash the micropipette machine instead, and you fight with Excel. All right, all of that is gone in the next years. You will not set up your standard Excel charts. You'll just ask for the numbers to be worked out for you, and that this is not future, this is past already. The pipettes still have to be washed, but that's what robots are for. And they will be here at an affordable price in not that many years or months. So many of the just traditional grunge work, whose main role is to teach you how science needs to be done and what are the actual activities so that you can generalize, those are going. How is it that we get people to learn enough themselves rather than telling a computer to do it, that they can learn taste, they can learn good, they can learn critiques? I'll come back to this, but this I believe is a critical issue. And I think back to my education, admittedly sometime in the Neolithic era, and many things that I learned by watching my advisor, who was a brilliant applied mathematician who didn't believe in computers. So, it was an interesting experience, but because I did, however, I learned an awful lot about perturbation methods. That actually was useful as a thinking process. And a critical set of issues here, what does it mean to be creative? What does it mean to be innovative in the sciences or many other fields? I'm not going to try to get into psychological theory or a long history of philosophic discussion, but there is a shift in how you should think about this in the scientific context. I mean, basically, computers are real good at looking at big search spaces, and much of creativity is looking one or two moves ahead. Well, computers do that real well. So how do we distinguish one form of innovation from another? And then, if computers can write papers quickly, decently, and fast, how do we count credits in science? I'm sorry that if I ignore all paragraphs that include the word H-index when I do look at personnel files or such. I know that's a bogus measure, but even I fall for the occasional citation claim. 25,000 people like this. 24,000 of them can't read, but doesn't matter. Or they're part of an auction ring, but I'll get to that later. Computers enable fraud in addition to helping you detect it. That's probably for a drinks conversation rather than an open auditorium one. let me take a tiny detour. I mean, I have the privilege of running an organization called Schmidt Sciences. It's partly a successor to earlier work. I have a basic, simple funding model. I ask Eric and Wendy Schmidt for money, and they generally say yes. And we give away a lot, actually. We finally admitted in last year we gave away about $300 million in grants out the door, dollars. So we try to support a lot of science. There's the AI and Science postdoc program, which, however, is only half of our postdoc collection. A nice extra part is, of course, the Schmidt Science Fellows, Megan and Matt here and some other colleagues. So we do a lot of this, but we support a lot of research and a lot of infrastructure to support research. And I'm proud to be able to do this. It's an amazing thing. And for later discussion, this is a very nice time to be on my side of the table rather than having to get grants. So no, I'm not offering any today. Please don't ask for over cheese. But now let me just move forward, if I may. So what are some of the aspects? I already mentioned literature search. I mean, basically, the LLMs, the ChatGPT systems are far better at doing the typical literature search than you will be. They've actually already read everything. They may not read it the way you do, but they've not only read it, they have literally ingested it, and you have rarely actually eaten the journals. So basically, you're crazy not to do that, and therefore, asking a graduate student to do a literature search is no longer a useful training exercise. You need to instead analyze something about the literature. And even there, it's getting tough. Data acquisition, lab automation means that it's possible for a university small group to do industrial grade data acquisition. And if you have the opportunity in some fields, you can tap into other people who are generating huge amounts of data. Schmidt Sciences is funding 4 new astronomical observatories. 2 of them will be ground survey instruments, and by about 2028, with luck, they'll be generating each 1 to 10 petabytes a year of processed information. This is an absolute gold mine for modern compute. And if I weren't here, I'd be involved in a conversation of what are we going to do smart about this. This is not unique. It's just I happen to be deeply aware of the flood that's going to start hitting us. And and it isn't just the bits are coming, but how do you analyze their quality? How do you ensure that you can guarantee their veracity, provenance, and security? All those classic questions are essential, but now there's the extra level of, and now how will I apply increasingly smart software to interpreting it, making the software making or evaluating hypotheses, and so forth. And data analysis, which in some sense is the core of experimental science. The part involving screwdrivers is, you can't get around, but what the real core is analyzing and understanding data. You would be crazy not to be having help from something that does arithmetic better and has probably a better understanding of statistics than most of you, with all due respect. Yes, I'm sure some of you are wonderful top-of-flight statisticians. The rest of us who are just competent statisticians, computers are smarter. I mentioned computer data. This is an area where my background happens to be astronomy, so I'm particularly fond of the work we're doing here. But you look at things like multi-messenger research. This means fusing data from multiple instruments that are looking at different sources, radio telescopes, gravitational wave telescopes, even neutrino devices. How do you combine these when the modalities of collection are different? The meaning of calibration is radically different. Your friend, the computer, is actually necessary for getting these things lined up and managed at scale. We don't have that many neutrino events. All the other ones are very large amounts of information and even more bits. And even if you're not, by the way, doing AI, if you're at the high end, you are using GPUs because nothing on the market will keep up with the large storms anymore. So a radio telescope that we are helping to fund, which will have an upfront data rate of a fraction of an exabit per second. I meant what I just said. And this has to be reduced rapidly to something that you can eat. We'll have 2 or 4 NVIDIA racks to make it happy. And that's before doing any AI on the reduced data. So a summary just from one of my colleagues who I asked for a bit of help here. AI is moving astronomy beyond automated analysis toward AI native observatories. Foundation models and adaptive pipelines are part of the observing chain, not part of the publication chain. And a project that we have funded, which is doing software to support users of the Vera Rubin LSST, which is just coming online in Chile, a magnificent survey instrument. NSF neglected to fund the middleware that is needed to make this easy to use, so we did. And there are pipelines that will keep up with the basic terabytes per second at high pitch when you're looking at some of the raw data, and allowing an astronomer not to do the hard distributed computing. And the code includes scalable data systems, yes, major pipelines. There's AI stuff needed to understand how to look at asteroids. Asteroids turn out to be difficult in this context because they move too fast. And the parameters of the Vera Rubin are such that if you see an asteroid, the next time you see it, it'll be in another part of the sky, given its field of view. And so now you need to combine pieces from multiple frames, each of which is a gigapixel. Okay, we've funded software that just does this. And Astro is clearly moving toward a world where there are just foundation models that do some of the best work. And now you start asking, what does the astronomer do with those tools? To be discussed. Let me take a detour on the role of theory. Those of us who had a physics type education, learned to love equations that we could memorize, like F equals ma, E equals mc, probably power 2, and after that, 3 is wrong. Okay. And nice short things. If you're getting annoyed, you have to remember all 4 of Maxwell's equations. Well, the real world isn't that nice. I'll mention climate models in a few minutes where, yes, the easy part is the Navier-Stokes core. The hard part is the weird physics approximations, and none of those are nice. Okay, AI allows you to parameterize those spaces if you do a large enough sample. And then you can do things quickly and not attempt to do microphysics at the micron level. But the real world complexity is there. Understanding the difference between analytic and numeric approximations. Yes, I know I'm dating myself, but I'm horrified to say that I recently looked at the n+15th edition of Jackson's electromagnetism, which apparently is still being used, and it still does series expansions. Excuse me, dumb. past the second term, nobody wants to see an E&M series expansion. Yes, you do need to know about quadrupole moments, but beyond that, you're just going to do a straight computation to get the answer. You're not going to get a lot more excitement by looking at the octupole term and for any known problem. Okay, education lags. But the distinction between understanding and usefulness. If you look at an equation that's this long, have you learned anything by looking at it? And are you smarter than if you just can do a 3 or 4D graph and explore it? As a simple example, that, no, don't even try to read it, that is the standard model. That's the Lagrangian of the standard model. And yes, it has over 100 terms. And that does describe particle physics to the state that we understand it today. And if you think you can get anywhere looking at that, you're wrong. Yes, I'm happy to say I do have a mug which has that picture on it, so I can stare at it occasionally. Yes, if you want, I'll show you a blow-up, but it won't make you any better because basically it's just got every gluon interaction, every boson problem, et cetera, has its own terms. All right, that says that real theory is better for computers to worry about, and for real understanding, you're only going to look at 4 terms anyway. Climate modeling, almost all of our knowledge of climate science actually comes out of climate models. Climate is, after all, so the standard definition is, climate is what you expect and weather is what you get. Whether that's a good computational problem works just fine. It's basically a repetitive initial value problem. These days, it is actually, however, better done by AI than by integrating Navier-Stokes. 2 years ago, that statement was false. Today, it is, I believe, true. And the main weather organizations are all moving to AI models on top of historic simulations. Well, when you look at climate, an obvious problem is that you can't look at the data for climate since climate discussions are about the future. And it's hard to get data about the future. And now, I'm not going to go into paleo modeling and such here, but yes, it's all real. But the computations that you need to do involve huge numbers of simulations, looking at uncertainties, looking at strange attractors. And to do that, you need to look at lots of models. Well, models are very expensive. AI emulators that look at a particular aspect of the climate that actually identify and ride on a lower dimensional manifold, not one with 10 to the 6 parameters, actually is almost certainly the way we will have to go in the next years, which says, despite various beliefs by some people here and elsewhere, huge HPC computations to do somewhat higher resolution integrations are not going to add enough extra knowledge. Basic fact, clouds are under a kilometer across on the average. So if you're going to try to distinguish clouds, you have to have a resolution of a fraction of a kilometer. Standard computing goes as n to the 3.5. This is bad. Okay, so this field is increasingly going to be dominated by solutions that have to do pattern match, that take advantage of GPU acceleration and so forth. So this field, I went to a workshop about 5 or 6 years ago where one brave person said that he had just done a small ML piece in a model of sea ice, I think, and had actually gotten some interesting results. And all the senior faculty in the room said, poo-poo, that'll never work. Now, that view and or those professors are now obsolete. Probably both. There's data is a big problem in climate modeling. You can't get data about the future. Getting data about the past turns out to be quite hard. We have satellite data going back 50 years. We have CO2 point data going back 75 years, and that's it. Well, So how do you get continuity? How do you do quality measurements? This is all very hard. And this has to be done no matter what your modeling approach is. But emulators at least allow you to look at large ensembles at a much more affordable price. You can do an emulation typically in 1,000th of the cost of an ab initio compute. So you can now therefore do an ensemble of 1,000 well-chosen, and now if you stratify your sample, you can actually learn something. Well, this is all radical change that has not yet penetrated the full field. Yes, we fund a lot of research in climate. I claim no personal expertise. I claim knowledge of people who have it. So anything I've just said that you disagree with, I'll tell you who to complain to. So we are already supporting some of this work. Interesting project on ice breakup, modeling ice flows. It turns out you have to model at a very fine grain if you want to understand how they break up. If you take a look at the pictures, the pieces that break are this big, and you're talking about an ice flow that's kilometers in size. So if you're going to simulate, you have to get all the way down there. This is, again, a sucker bet. Modern computing allows you to build a much better agent solution that gets much closer fidelity versus real images. And this is a project we were funding in, I believe, Norway and France that's getting these results. Similarly, emulators that are using just a few GPUs are getting results that are of comparable quality to some of the very large-scale computes. And these are just results that have come in the last 6 months for projects that we're funding. So, what are some of the bigger topics in accelerating science? Well, I'm not going to go through all the lists here. One point here is this is not a marketing story. I lived through the expert system era of AI, and I noticed after a year that the same 3 stories were the only stories anybody seemed to tell. And that turned out to be approximately right. That new and amazing stories of AI applied to real science problems come in every week. Open Nature, if you want. They specialize these days in publishing those nicely. So AI has an increasing scope of what it's going to do for scientists. And basically, there's some areas where that's just a given. Helping you write your paper, yes, you may have to check a box that said, yes, an AI helped, but why not? Unless you are proud of your English prose, let the computer help you on that. And by the way, if English is not your native skill, it's unfair not to do it. And so I'm absolutely opposed to rejecting use of writing assistants. It's just levels of playing field that's not relevant to science itself. Supporting experiments, ongoing calibration, ongoing operation, recognizing patterns. Computers are simply better than the average person once you get up above scale of looking at 6 things and want to look at 6,000. You can't recognize those data looking at a printout. Computers can, and the computers that have a big AI boost do it far better. The world of scientific publication is in a revolutionary period or disaster, take your choice, depends which side of the fence you are. Open access journals turn out to be the finest source of modern fraud of almost anything that's been invented. There are estimates that half of the journals are basically bogus, and they have names that are awfully good sounding. Okay, so first of all, so the literature is polluted. The ability to generate interesting but not wonderful papers at a very high rate means that the review processes, the serious critiques are no longer feasible. It's been a long time since any of my friends have said it was reasonably easy to get reviewers. Even the most prestigious venues are in trouble. And when you look at things like the NeuroIPS conference, they have 500 to 1,000 reviewers, and then they have an amazing amount of cross-checking for honor among the reviewers. Okay, meta problems stack up layer by layer in this world, and nobody that I know has an intelligent answer to what we're going to do with the increasing flood of publications where nobody can verify that they're excellent, and nobody will spend the time checking that they're accurate. Well, so an H-index of a zillion is not impossible if you're a robot, and you carefully arrange a citation ring. I've spoken to publishers who are really worried. We are funding software for archive, and they are seeing a flood coming in, and even though they do only a light review just for base validity, they're being swamped. And that's where there's no claim the stuff is right, only that it looks like science. Looks like, sorry. Well, these are big changes in the doing of science. All of us have been trained in the purpose of doing scientific research is publication in a journal, basically. That's the measure of what you did, and then you hope it meant something later. Well, that mid-stage is now being denatured and, sorry about that, de-scienced too. But what are we going to replace it with in this model? Those of you who are senior academics and who are used to weighing the published for a promotion candidate and now know that half of those are written by a bot, the better ones maybe, how are you going to decide on promotion or keeping people? These changes are happening at, by normal standards, lightning speed. The changes are happening to us rapidly. And in the lifespan, in the education span of a single graduate student, the rules are being rewritten on what it means to do science in many fields. And in another 5 years, the rest will also be affected. If you want some interesting reading from the Leiden Declaration on AI and Mathematics, which is a manifesto published yesterday or 2 days ago, is an interesting piece, and I recommend it to you because it's an attempt to grapple with the question of what's happening to my field and who's going to verify that the theorems are correct. Well, actually, the computers are better at that than people. They don't admit that in this declaration. However, what does it mean to do advanced research? What does it mean to be training for learning for impact of your mathematics, not just the magnitude? Nobody actually has a good feeling, but I commend this because it's actually written by smart people, and it's as fresh as it gets. It's just Leiden Declaration Mathematics search will find it. Quality and integrity, oh boy. This is a long-standing core issue. I'll just remind you of the cat fights between Newton and Hooke and Leibniz about priorities and who was cheating about their publications. And in the good old days, people like Mersenne, who acted as a network publishing mechanism, one of the real reasons for sending Mersenne or the Royal Society an article was to claim priority, not to actually get anywhere. Well, now let's move forward 3 centuries, and now let's speed up the act by 10 to the 12 and ask, how are we going to detect integrity? How are we going to follow this up? Sadly, I will just say that Schmidt Sciences has grown a lot in the past few years, and I now have about a half dozen significant fraud issues of one of almost every form that have hit us or our grantees or awardees. Well, This is just a microcosm, and these are the ones we know about, of course. I will assume there are others. Well, I've already mentioned the questions of career path. In many countries, publication records are necessary explicitly for keeping your job, not just getting promoted. This provides wonderful incentives for fake papers, fake publications, citation rings, and so forth. And we already have those only working with people up to 2 years ago. Now these are much better done and much better automated. I think that we can assume a continuing drop in the integrity of the publication record and in the publication claims. How are we going to fix this? Well, AI is probably the only tool we've got for improving this, but the cops are behind the thieves at the moment. And these are all issues. But in addition to just dishonesty, let me point out things like speed of dissemination. If papers are being written overnight rather than over a month or 3 to get them right, then the competition level is intolerable, and it's already there in many fields, especially incestuous fields like AI itself, where publication happens after not that many hours after somebody does something. Well, coming back to astronomy, traditionally, in the good old days, astronomical plates were the property of the observer. The astronomer would go up the mountain, take pictures on photographic plates, and put the photographic plates in the station wagon and take them back to his university. Yes, it was always his. Separate history on sexism in astronomy. But now, I have stated that for the instruments we're funding, my preferred embargo period for data is under 100 milliseconds. This means that although you may have requested an observation, everybody on the planet will get to see the data about the same time you do. How do you then get priority on the results of this? Well, you better be fully prepared with the analysis techniques and the science before this happens. Well, this means you don't get to sleep much if you're on the leading edge. These are real changes. So, again, I'm not going to go through all the cases, but so that slide is a duplicate. Let me just talk a little bit about creativity and inspiration. Most of us are in science because there's something exciting about something new, a discovery, an understanding, a new fact about the universe, or a new understanding about how something happens. That's what we like. Well, what is originality? Well, let me just go back to the examples of chess, where the major chess machines have generated wholly new attacks, wholly new ideas of how you play chess. It's not just that they beat ordinary masters. They do things that humans had never done before. Is the computer now being original and creative? Well, we have decided that that's never the right answer, and so we moved the bar on what is creative. It's going to be true in science, too. We're going to redefine where the creativity line is. Today, you know that there have been some rather interesting steps forward in automatic, not just theorem verification, but theorem proving, where unproved conjectures have actually been first done by a computer system. The past few months, there's a heavily publicized case of an Erdős graph theory problem, where 2 different bounds that were produced by 2 different science systems. And this problem had never been cracked before. Now, in fairness, Paul Erdős used to solve an Erdős problem approximately once a week. He has published like 1,700 papers, and each one was a solution of some problem. So, okay, we haven't caught up with Erdős yet. However, what is it going to mean to be creative here? And to the extent that creativity in a field like mathematics is combining pieces that didn't seem to be connected before and now are, and that is, if you go and ask what was amazing about Wiles' proof of the Fermat conjecture, it's the number of areas of unrelated mathematics that got pulled in that nobody else knew, basically. Well, your friend, the computer, knows all of those to the extent of having ingested those papers. What's going to be the next generation of creativity and originality, and how are we going to redefine it? There's the old line that engineering is 99% perspiration, 1% inspiration. Of that 1%, what fraction of that is going to turn out to be computer-based perspiration, leaving you with 1% of 1% that you will call creativity? I don't know how this is going to play. This is a clear morale problem for all of us who are excited about doing science and learning science. How are we going to get our heads about the changed world, the way we will use computers, and try and believe that the computers aren't using us to solve new problems? So again, this is pure speculation, but I'm not talking about 50 years. I'm talking about 5 or 10 at the most until this is on us fully. So those of you who are undergraduates, if any, by the time you are entering the research world will have changed a lot. Well, at one level, that's good. Let me just mention, I should be stopping sometime soon anyway. Let me just mention the roles of institutions and how they're shifting. Government has, for a while, basically since the 1940s, been major funder and driver of most of scientific research. Before that, it was mostly philanthropic, but therefore much smaller. On the other hand, one of the founding documents called The Endless Frontier by Vannevar Bush, published in 1945, many of us love the picture that he drew. Unfortunately, that era ended about a month ago, literally. I'll go into detail if anybody wants. However, if you go look at the budget he proposed for the American science budget, it was, I believe, $60 million to rise to $120 million. And even with good old inflation corrections of an order of magnitude, you're still talking about an American science investment of $1 billion a year. Well, we're off by 2 orders of magnitude. Okay, so that's the good news. But government has, in certain areas, been the shaper of the agenda, the provider of use cases, the puller of applications. Well, in the age of AI, with the changing needs, the changing opportunities, the changing costs, government is not yet there. There's something called Project Genesis, Department of Energy in the US. Let me rephrase that. With luck, there will be such a project since it is not currently funded. And the funding level planned is a few billion, which sounds good until you realize that doesn't buy you all the GPUs that they're promising. The plan is a 10,000 GPU machine this year and 100,000 next year. 100,000 GPU machine costs around $5 billion. A month ago, prices may have doubled in the past month, and I'm not joking. It's a crazed world. Industry, well, traditionally it provides hiring, it provides jobs, it provides the application of results for tomorrow. Industry is basically the steward of execution knowledge, both tacit and formal. How do you actually get something done in the world? Well, in many fields, in practice, industry has been the driver of innovation. Academics do not like this part of my usual speech, but in many areas other than the purest sciences, the real innovations have come from companies. And then the understanding of why they worked came from the classic research world, looking at what, after you have some successes, you figure out why those are the good ones. Well, in AI at the moment, an embarrassing fraction of new steps forward are coming from the top 5 or 6 companies, partly because they have the computers available, partly they have the applications, and partly they cherry-picked a lot of good people out of the rest of the world. Okay, this is not a stable or self-sustaining world. It will shift, but this means that the normal assumptions about where the smart people are and where the leading edge is no longer automatically that you'll find it within 100 meters of where I'm standing, which would have been the answer 30 years ago. Well, on the other hand, most of advanced research does happen in universities around the world, most especially in the best ones. Yes, I'm familiar with the long-term ranking of Oxford. Yes, I met with the Vice Chancellor a few hours ago, who reminded me, of course. Yes, I know, top number 1 for 10 years running in the THE ranking, and probably deserved to. So that's good, but I will not ask an invidious question, and pardon the pun, but how many GPUs does this campus have for its own use? And by the way, where are you going? If you wanted to buy them, how would you power them? Well, this is a problem. And without this capability, you can't be leading edge on some of these areas of science. Many things you can do with 1 or 8 GPUs, foundation models, fundamental language models are all run at the moment at least, in the thousands of GPUs for multiple months or fractions of a year allocation. That's the current entry for being at the top edge of certain aspects of AI and for being able to lead in use. One of our grantees, Shirley Ho, has, so far as I can tell, been able to get almost all of a French supercomputer for herself for about 6 months, and has done absolutely amazing work on basically generalizing fluid mechanics to cover half of physics. I can discuss more about that. Quite amazing work and very expensive, I know, because we fund a bit of it. And then, and then there's people like us, philanthropy. Well, we're an independent player in many ways. What our advantage in the American and British scene is that we are not required to just do that which a government agency wanted to fund or universities were already doing. So, we may not be right, but we're different. And this adds a certain degree of, take your choice, randomness or serious variation in the whole scene. And bluntly, we act faster than, yes, I'm not going to say we don't have bureaucracy, and that's for drinks. Even an organization like mine can have trouble getting out of its own way. But astronomical observatories and space systems typically have decade or multi-decade timeframes. Our approach for the observatories we're doing is less than 4 years from actual green light to first light, and we're expecting it to happen. So we may not have the resources, we certainly don't have the resources of, let's say, the NIH, or anybody else have the resources of the Wellcome Trust, which is a government-size agency, unique. But we get to choose problems and push them. In AI, we are focused on a bunch of interesting niche problems. I find myself funding a surprising number of humanities and AI projects, a number that is larger than probably any other American funder, not because we're wonderful, but because of politics has wiped out other supporters. By the way, I'll just mention without any further detail that the project that actually gives me the most pleasure that I have okayed in the recent past is one that will be pushing very high-tech techniques applied to alchemy. So Schmidt Sciences is supporting probably the best alchemical research of the recent past. It makes me feel good. Yes, if they're throwing LLMs, quantum simulation, and automated labs at 15th century recipes. Okay, well, no sane organization would be doing that, and no sane organization with the name science in its title would. We can and we should. Well, all right. But we're also funding a lot of very hardcore work on trustworthy and safe AI. It turns out that there are all kinds of scary ways that modern systems could get you in trouble. And understanding the fundamentals under that is very hard. Companies who are trying to sell you on AI have a limited desire to spend lots of their best resources on this problem. So we and a couple other philanthropies are doing that. I've gotten very tired of the many essays on how AI is already killing the job market or how it will kill the job market. And it is amazing how many essays you can write without a fact. Well, we're funding about a dozen randomized trials to see if we can actually get some current facts on what AI systems are doing in various aspects of the labor market. And it's not all the obvious American cases. One of the projects is looking at how automation is changing the loan origination in, I think, Sierra Leone. Okay, yes, we are global in many ways. So we're prepared to fund things like that because it's not actually in the interest of most people to fund it. And we're not unique, but this is an area where philanthropies can operate on a different time scale. We can get things going sooner. We can decide to fund things longer if we choose. So again, do not come up to me over drinks with a proposal, please. I don't have any space in my luggage for it. However, we are funding a lot and will continue to fund. And we do mostly open calls, very competitive, classic reviews. And boy, do we get applications. The last humanities call brought in 500 proposals. The most recent safety call brought in 750. And these are all technical proposals, not 2 paragraphs. So deciding, and we're only giving 5 or 20, depending on the program, grants. And the quality of the proposals has risen radically in the past few years. A few years ago, I counted on throwing out about 1/3 of the incoming as being just garbage, not relevant to the call or not literate enough to read. And now the bench rejects are under 10%. People don't bother us with things that are unrelated. Okay, so we have a pick of wonderful projects. Do we choose the right ones? Who knows? We'll find out in a few years when they mature. So let me, I'm not going to give a long spiel about the pleasures of being the sponsor here. I'm very happy that we are sponsoring a number of projects and programs here, as Nigel mentioned. And they were not given to Oxford simply because we felt like giving to Oxford, but because Oxford proposals won the quality mark. And looking forward to more such serious successes coming. And If you want to talk about things we do, you can look at our website or ask me questions. So let me just stop and just say, we live in extremely interesting times in the sense of the traditional Chinese curse. These are very interesting times. And some of the things are going to be positive and some not so much. I'm sure that there will be enormous shifts in both scientific output and our understanding. We're actually going to have much more understanding and knowledge resulting from the scientific work in the next 20 years than we would have had in 100 years without this revolution. On the other hand, there will be rifts in the fabric of the scientific enterprise. Who's doing what? Who is being recognized for what they did? Who can keep up given the time scale and or the resource access? And this is going to be an interesting battle. Many of the mechanisms that we count on in science are simply going to have to be replaced. The world of publication is in a world of hurt already, and it's going to get much worse. But our goal fundamentally, and I hope yours, is to accelerate the positive outcomes, mitigate the harms, and enjoy doing this differently. So thank you. And that was the standard model, which nobody can read. So yes, I can also give papers with equations in them if I had to. So.
Stu, thank you so much for awesome.
Thanks for that talk, Stuart. So I've spent the last 25 years devising training programs to train PhD students at the interface between traditional disciplines, the mathematical, physical sciences, and life, environmental, and medical sciences.
Mm-hmm.
So given the challenges that you've described, what advice would you give us on what we should focus on in changing those training programs so that our students continue to be at the forefront of their discipline?
I think you'll be hardly surprised that I will give an argument about cross-disciplinary knowledge and understanding, that there should be training that tells you the different aspects of different sciences so that you can actually judge what's good when you cross-breed them. Assuming that your physical laboratory setup will be radically different in 5 or 10 years, that you'll be doing far more work based on massive data, and therefore training people to understand how you extract understanding, not just information, from complex data. Once you get into the world of bio, the data are a mess, because biology is a mess. Spend 1 billion years evolving and you get strange things, no surprise. And nobody thinks that there's an F equals MA. Well, so I would be focusing on people learning to think in more than one way and to have a way of understanding what the computer and they are doing together. But there's a radical change in capability that's already here. And I've had a couple fascinating discussions with some senior colleagues in the past few months, and I'll summarize the conversation in at least 2 cases. They were actually sitting down and actually trying to do some real work, even though they're very senior. They were actually trying to calculate something using real data and real physics. And they decided to use the computer rather than pencil, as it were. And yes, they got results much faster than they ever would, but they were also both shocked at the advice they were getting from the computer about the fundamental science. The computer was recognizing some of the science answers, not just writing Python code for them. I asked then, since one of them was, they were both from top 3 universities in the world. Wouldn't they have preferred just to have one of their usual grad students at their next to them instead of Claude? And after deep thought, both of them said no. Oops. Okay. So figuring out how you're going to bridge that so that they get quickly to the point that they don't need their old graduate student and their new graduate students they do want. That's, let me suggest, a real challenge. And yes, I was a graduate student, I understand.
A lower brow question. With your funding into AI research, etc.
I'm sorry.
With your funding into, is it working? Yeah. Do you think demand for AI chips and supply chain issues, such as shortage of helium for the factories, etc., do you think that's going to affect for yourselves and people researching the supply and costs of getting AI processing?
Let's see, the price of flash solid-state memory has only gone up a factor of 4 in the last 3 months. Supply chain, thank you. And lots of people with lots of money wanted it, and that's a good way to, it's good to be a supplier in that environment. Getting large amounts of power is very hard. You know, we're planning to install a number of GPUs which will eat 5 or 10 megawatts, which is not a lot by this standard, but we have luckily found an institution that happens to have excess power because of something they got rid of. Otherwise, it would have been taken us 2 years to go pay for a power supply. Yes, these are very real binding constraints on the real world. I was speaking to somebody a few days ago who was regaling me with his negotiations with an otherwise friendly government on how he was going to get a fraction of a gigawatt and how many years it was going to take. Yes, these are very real. And I don't want to get into the debate about whether this is burning up the planet or such. I'll just say that if you do climate research using this, you're likely to save the planet much more than you're likely to heat it. But it's easy to say that since I don't have to pay for it.
Perhaps the alchemy research will help.
Well, I do insist that if they find the Philosopher's Stone, that the results be open source. All of us should be immortal.
Hello, is this on? Okay. First of all, thank you for the talk, and I appreciate the astronomy callouts as someone who's in planetary science and spacecraft missions. So in that field specifically, we've historically been so data-starved and that's going to change rapidly, that the applications of AI are fairly obvious, I would say.
Mm-hmm.
That being said, as someone who is a numerical modeler, the skills that have set me apart are going to quickly become fairly obsolete. So my question for you kind of concerns how we try to get ahead of that. Because I think it's very obvious, or I shouldn't say obvious, you talked about several different applications, how we can use AI as a tool, but it feels in some ways somewhat reactionary. It's essentially trying to stay abreast of the wave rather than being drowned by it. How do people like me try to get ahead of that wave?
Being smarter and more energetic, that's a good start. Sorry, I assume you're both. But honestly, everybody will be using a certain set of tools by default. One reason that we are funding the LSSTC effort is so that everybody gets to use the same set of decent middleware rather than write bad stuff themselves. If they want to write better, bless them. They can enjoy the pleasures of distributed pipelines. There are very few pleasures, I mean. But thinking hard about what are the analyses you need to do, what are the aspects you're looking for, what are the weak signals that suddenly you can pull out. I can discuss some recent work that one of our projects at Johns Hopkins has been doing, pulling out amazing amounts of spectral data from truly wretched data, because it turns out that you can be very smart using ML to pull out signals that you wouldn't think were there. Okay? Smart, energetic, and trying again.
Thanks.
And we're about to fund over the next few years 15 small groups to do astronomical research with a goal that they will think of things that would be uniquely useful using at least some of our instruments plus others, so that they will kickstart the efforts. But there will be no secret knowledge about these devices, and anybody else who wants to plan in advance, go ahead.
Great, thank you.
It's just getting harder and harder to be number one in the queue. I'll let you manage the audience.
Thank you. I think it's like point taken. This is very useful for a lot of
Can you
things.
talk a little louder?
Sorry, can you hear me?
Now I can.
Yeah, so I was just wondering if this is very useful for a lot of different things, and I was just wondering if you find that it shouldn't be used for anything. Like, have you noticed any field in which you think this is not very good at or not?
I'm sorry, if computers are going to be good for alchemy, there are not many fields that won't be affected and revolutionized. I'm sorry. So yes, mathematics is clearly number one in the chute. The lean work and such is all wonderful. How the learnings from that will be applied, I don't know. Generalizing the protein folding stuff to other problems is moving slowly, but it probably will move with heavier AI. So, and these are radically different problems. So I'm not willing to predict anything that's safe. Probably the only thing that's safe is actually generating some of the data from unique instruments. Just because if unique means you're the only one doing it. There are areas which are clearly at bigger risk than others, but that's a 5-year story or a 5-month difference, not a 50. And I'm assuming that people like you are looking at a longer time frame.
Thank you for the talk. It was really validating and encouraging, and I like the level of critique you have with AI. It's good. From an astronomy perspective, particularly radio astronomy, for the radio array, the large radio array that is being funded by Schmidt Sciences, in terms of the data products that are coming out, obviously is a problem. SK is having the same problem. Are you planning on storing the raw visibility data, and or are you planning on doing data reduction in real time? And would you be using AI in the data reduction pipeline?
Okay, let me try to and give the specific answer with respect to the telescope we're funding, which is what used to be called DSA 2000, except there's only going to be 1,600 antennas. They're just bigger surface area, smaller number of antennas. The upfront data rate is several hundred petabits a second. Nobody is storing that. Nobody can store that. 1,600 antennas means over 1 million interferometers simultaneous. Okay, so the question is, which stage do you count as storing the raw data? And yes, we will be doing some of the snapshots once it's down to, I think, the 40 terabytes a second phase. Before you do the inversion of the matrices, so you can do the multiplication. And we will plan to store for a long term the stuff that comes out the back. The DSAs will do a picture of the sky, not just a Fourier version of it every 15 minutes per field of view. And so it will be producing terabytes a day, and those that will be both stored and distributed immediately. However, again, one stage up, there will be snapshots, and there are likely to be some areas of the sky that are looked at many times because we'll probably be supporting one or more of the pulsar efforts which want to come back to the fields. Sorry, I'm boring all of you, but 3 people, sorry. Yeah, I really do like astronomy. And I haven't had this discussion since yesterday night. Okay, but okay. So, and similarly, we will be having an optical survey instrument, Argus, which will be doing basically a sky image down to 19th magnitude every 15 minutes. And when you co-add over a week, it'll have a sky image, full gigapixel plus for 23rd, I think. Okay, yes, now how much of this will we store and how do you decide? This is going to be an interesting free-for-all, and experts thinking about this, please apply. Thank you.
Actually, I'm just going to use this one, if that's all right. So, good evening, everyone, and thank you all so much for coming to this special event. My name is Kate Newport, and for the past 2 years, I have been an Eric and Wendy Schmidt AI and Science Fellow here in the University of Oxford. I study animal behavior in fish, and in my research, I'm trying to understand how fish are able to navigate in underwater systems and how they can do it even in really low visibility conditions where current autonomous robotic systems cannot even navigate. So the Schmidt Science Fellowship has given me the training that I've needed to apply to the art of computer vision and AI tools to create 3D reconstruction underwater and to begin identifying the navigational algorithms that fish use. So rather than going from large AI systems, let's understand what a really tiny brain, the equivalent of maybe a calculator, can do in a system where autonomous systems don't work. So it's my great pleasure tonight to thank our speaker and Schmidt Sciences. So Professor Feldman, thank you for a truly enlightening lecture. I don't know if I'm terrified or excited for the future at this point. Yeah, both are good. And thank you for so generously sharing your time, expertise, and reflections with us this evening. On behalf of everyone here, thank you not only for today's lecture, but also for helping to stimulate the conversations, ideas, and research that will continue long after we leave this room tonight. I would also like to express our gratitude to Schmidt Sciences for its continued support of research and innovation here at the University of Oxford. Now, the opportunities created through this partnership, including the AI and Science Fellowship, have truly had a profound impact on researchers here. As a fellow, I've had experience firsthand seeing how we've all been able to pursue these really ambitious programs of research and build new collaborations and explore new tools. So this program has already supported a remarkable cohort of fellows, and many of whom have gone on to faculty appointments, senior research fellowships, or even industry. So I think that by bringing together researchers from these different STEM fields and enabling them to apply and understand all these new AI methods, it's really helping to lay the foundation for the next generation of scientific discovery. So thank you so much for that, and to Schmidt Sciences. Of course, my thanks go out to the team here at the Sheldonian Theatre for hosting us in one of Oxford's most iconic buildings, to the DTC team who has organized this event and done such a great job in delivering tonight's talks. And finally, thank you to all for joining us this evening. Your presence, engagement, and participation have really helped make this a memorable occasion. So please join me once again in thanking Professor Feldman.
Thank you for that excellent summary of what we were trying to achieve with this program.
Well, I'm so glad, and hopefully I'll see you at dinner tonight. We can chat about fish brains.
Or eat them.
Or eat them.